Magnetism is one of those phenomena that feels completely ordinary until the moment you stop and really look at it. From childhood, magnets are introduced as toys, as harmless objects that snap together or stubbornly refuse to touch. They feel intuitive. You bring two magnets close, they pull. Flip one around, they push away. Nothing about this seems strange at first. And yet, buried inside this everyday familiarity is a mystery so deep that even the most brilliant physicists hesitate before answering it. The real puzzle does not begin with advanced equations or laboratory experiments. It begins with the false comfort of simple explanations. Most people grow up hearing that magnets work because they have north and south poles. Opposite poles attract, like poles repel. This statement sounds like an explanation, but it is not. It is a rule. It describes what happens, not why it happens. If someone asks why opposite poles attract, repeating the rule in different words does not move us any closer to understanding. We simply circle the same idea, dressing it up with labels that feel scientific, but hide the emptiness underneath. Richard Feynman was especially sensitive to this problem. He understood that human beings crave explanations that fit into everyday intuition. We want mechanisms we can picture: gears turning, strings pulling, tiny hands reaching out and grabbing. Magnetism refuses to cooperate with this desire. There is nothing visible stretching between two magnets, nothing you can point to in space and say, "That thing right there is doing the pulling." All you see is motion without contact, influence without touch. For a mind trained to understand the world through direct physical interaction, this feels deeply unsettling. At first, people often invoke the idea of a magnetic field. A magnet creates a field around it, and that field affects other magnets or certain metals. Again, this sounds satisfying until you realize the field is invisible, intangible, and defined entirely by how it influences other objects. If you ask what a field actually is, you are usually told it is something that fills space and exerts forces. But then another question appears immediately. What does it mean for something to fill space without being made of matter? How does empty space suddenly gain the ability to push and pull? This is where Feynman's critique becomes sharp. He pointed out that many explanations in physics are layered abstractions. Each layer works beautifully for calculations and predictions, but none of them provide the kind of story people instinctively want. When someone unfamiliar with physics asks why magnets attract, and you answer with, "Because of magnetic fields," you are assuming the listener already accepts fields as a fundamental part of reality. If they do not, the explanation collapses. You are no longer explaining, you are asking them to take something on faith. The everyday mystery of magnetism lies precisely here, in the gap between description and explanation. We can map magnetic fields, measure their strength, and predict their effects with incredible accuracy. We can build motors, generators, hard drives, and medical scanners based entirely on these predictions. Yet if someone insists on knowing what magnetism is in the same way they know what pushing a door is, physics falls silent. Not because it has failed, but because the question itself assumes the universe must be understandable in human terms. This tension becomes clearer when we compare magnetism to something like gravity. People are used to the idea that gravity pulls objects together, but gravity also acts at a distance, without visible contact. Historically, this troubled scientists as well. Newton himself was uncomfortable with the idea of action at a distance. He could describe gravity mathematically, but he refused to speculate on its ultimate cause. Magnetism shares this unsettling quality. It works, it can be measured, but it does not offer a comforting picture of little pushes and pulls. In everyday life, magnetism feels almost magical. A paper clip leaps upward to attach itself to a magnet. Iron filings arrange themselves into elegant patterns that seem to reveal hidden lines in space. These demonstrations suggest something real is there, something structured and active. And yet, nothing is actually visible. The filings merely trace the influence of something we cannot see. This creates a powerful illusion that we are glimpsing the machinery behind the curtain. In truth, we are only seeing the effects, not the mechanism itself. Feynman often emphasized that physics progresses by giving up demands for certain kinds of answers. The demand that every phenomenon be reduced to a familiar picture is one such demand. Magnetism forces us to confront this limitation early. Even at the level of classical physics, magnetic forces do not fit neatly into mechanical analogies. They depend on velocity, direction, and orientation in ways that defy simple storytelling. When electric charges move, magnetic effects appear. When they stop, magnetism changes. The force depends not just on where things are, but how they move through space and time. This already strains intuition, but the mystery deepens when we realize that permanent magnets do not rely on currents flowing through wires. They sit quietly on a table and still exert magnetic influence. This raises a new everyday question: what is moving inside a magnet? What is sustaining this invisible power? Early explanations imagined tiny circulating currents inside atoms. This picture worked well enough to guide research, but it was still a metaphor, not a literal description of reality. The real source of magnetism turned out to be far stranger than anyone expected. It lies in quantum mechanics, a theory that already challenges everyday reasoning at every step. Electrons possess properties that have no classical analog. They behave neither like tiny spinning balls nor like waves in the usual sense, yet they exhibit characteristics of both. Magnetism emerges from these abstract properties, combined with the rules that govern how electrons are allowed to exist together inside matter. From an everyday perspective, this explanation feels like a betrayal. We started with a simple question about fridge magnets and ended up in a realm of probabilities, wave functions, and mathematical symmetries. The distance between the question and the answer is so vast that it feels almost unfair. Yet this is exactly the point Feynman was making. Nature does not organize itself around human convenience. The deepest reasons behind simple observations often live at levels of reality far removed from daily experience. The everyday mystery of magnetism is not just that magnets attract or repel. It is that the universe allows such interactions at all. There is no obvious reason space should have properties that permit forces to act across it. There is no intuitive necessity for matter to organize itself in ways that produce stable magnetic domains. These facts are contingent. They are features of this universe, discovered through experiment, not deduced from logic alone. When Feynman spoke about magnetism, he often returned to the idea that physics is about describing how nature behaves, not about satisfying philosophical cravings. Asking why magnets work in a deeper sense eventually leads to questions about why the laws of physics are what they are. At that point, science reaches its boundary. We can test laws, refine them, and sometimes unify them, but we cannot step outside the universe to explain why it chose one set of rules over another. This does not make magnetism less wondrous. In fact, it makes it more so. Every time two magnets snap together, they are silently expressing layers of physical law that stretch from everyday experience down to the foundations of quantum theory. The simplicity of the observation hides the complexity beneath it. What feels like a trivial toy is, in reality, a window into the deepest structure of matter and space. The danger lies in mistaking familiarity for understanding. Because magnets are common, we assume they are simple. Because we can name their behavior, we assume we have explained it. Feynman warned against this complacency. He encouraged curiosity that goes beyond labels and challenges comfortable assumptions. The mystery of magnetism is not a failure of explanation. It is a reminder that the universe is under no obligation to align with human intuition. In this sense, magnetism becomes a lesson in humility. It teaches us that even the most ordinary phenomena may rest on principles that resist visualization. It reminds us that science advances not by inventing stories that feel right, but by discovering rules that work, even when they feel strange. The everyday mystery of magnetism is not meant to be resolved into a neat picture. It is meant to be appreciated as evidence that reality is richer, deeper, and more surprising than our instincts suggest. And so, when we ask why magnets work, we are not just asking about a physical force. We are asking about the nature of explanation itself. We are confronting the limits of human understanding and learning where description ends and mystery begins. That moment of discomfort, when the simple answer dissolves and a deeper question appears, is exactly where physics becomes most honest and most beautiful. When people ask questions about nature, they usually expect answers that feel like everyday reasoning stretched a little further. They imagine that if something is mysterious, it is only because they have not yet been told the right story. Once the story is told, the mystery should dissolve into something familiar. Richard Feynman strongly disagreed with this expectation. He believed that many of our deepest misunderstandings about physics come from demanding answers that match common sense, rather than accepting that nature operates on principles that may never feel intuitive. Feynman often used magnetism as a perfect example of this problem. When someone asks why magnets attract or repel, what they usually want is a picture they can hold in their mind. They want to imagine tiny hooks, invisible strings, or flowing substances that connect one magnet to another. This desire is natural. Human understanding evolved in a world of direct contact, where causes and effects are visible and mechanical. Push something, it moves. Pull it back, it returns. But magnetism refuses to play by these rules. There is no touching, no visible connection, and no clear mechanism that resembles everyday experience. Instead of trying to force magnetism into a familiar framework, Feynman challenged the very demand for such a framework. He pointed out that common sense is not a reliable guide to how the universe works. Common sense is shaped by a narrow range of experiences at human scales of size, speed, and energy. The atoms inside a magnet do not care about human intuition. They follow rules that were written into the structure of reality long before humans existed, rules that only reveal themselves through careful experiment and mathematics. When Feynman explained physics, he often began by exposing the weakness of so-called simple answers. Take the phrase magnets attract because of magnetic force. On the surface, it sounds explanatory. But if someone asks what a magnetic force is, the explanation quickly unravels. A force is defined by what it does, not by what it is. It causes motion, acceleration, or resistance. Saying that magnets attract because of a force is like saying that sleeping pills work because they have a dormitive power. The explanation merely restates the observation in different words. Feynman's challenge was not to dismiss questions, but to sharpen them. He wanted people to realize when they were asking for a description, and when they were asking for something deeper. Many why questions in physics are really requests for analogy. They are asking, what familiar thing is this like? But not everything in nature has a familiar counterpart. When physics reaches the level of fundamental laws, analogy runs out. At that point, the best science can do is describe patterns and regularities, not provide comforting narratives. This is deeply uncomfortable for many people. It feels like an evasion, as if physics is refusing to answer. Feynman argued that the discomfort comes from unrealistic expectations, not from a failure of science. Physics answers questions by telling us what will happen under certain conditions and with what precision. It does not promise to translate those answers into everyday mental pictures. Demanding that it do so is like demanding that a map smell like the territory it represents. The map's job is accuracy, not familiarity. Feynman also emphasized that common sense is not fixed. What feels intuitive today once felt absurd. There was a time when the idea that the Earth moves around the sun contradicted everyday experience. People felt the ground beneath their feet and concluded it must be stationary. Over time, with evidence and explanation, this once shocking idea became part of common sense. In the same way, many aspects of modern physics feel strange only because our intuition has not yet caught up. However, Feynman was careful to point out that some things may never become intuitive in a human sense. Quantum mechanics, which underlies magnetism, does not just stretch common sense. It breaks it. Particles behave like waves, probabilities replace certainties, and outcomes cannot be predicted with absolute confidence, only likelihood. Trying to force these ideas into classical pictures leads to confusion rather than clarity. Feynman believed it was better to accept strangeness honestly than to hide it behind misleading metaphors. When discussing magnetism, he often highlighted how misleading everyday language can be. Words like pull, push, and field carry baggage from ordinary experience. They suggest substance, contact, or motion through space. In reality, these words are placeholders for mathematical relationships. A magnetic field is not a physical thing waving through space like smoke or water. It is a way of summarizing how objects would behave if placed in certain positions and states of motion. Treating it as a substance leads to false intuitions. Feynman's challenge extended beyond magnetism to the way people think about explanation itself. He argued that explanations are always relative to what the listener already understands. To a child, explaining magnetism in terms of atoms might feel satisfying. To a physicist, atoms themselves demand explanation. To go deeper still requires quantum theory, and beyond that, even quantum theory rests on postulates that are accepted because they work, not because they feel obvious. At no point does the chain end in something self-evident. This relativity of explanation means that common sense answers are not absolute truths. They are temporary stopping points. Feynman wanted people to recognize when they had stopped too early and mistaken a label for an understanding. Calling something a magnetic field feels like an answer only if one forgets to ask what a field truly represents. His approach was to keep peeling back layers until nothing but the fundamental rules remained, and then to admit honestly that those rules simply are. There is a kind of intellectual courage in this admission. It resists the temptation to invent comforting stories where none exist. Feynman believed that pretending to understand is worse than admitting ignorance. Saying this is how nature behaves, and we don't know why it chose this way, is not a weakness of science. It is one of its strengths. It leaves room for further discovery and avoids freezing understanding into dogma. In challenging common sense answers, Feynman was also protecting curiosity. Simple but misleading explanations often shut down deeper questioning. If someone believes magnets work because they have north and south poles, and that is the end of the story, they are unlikely to wonder further. But if they realize that this explanation is incomplete, curiosity remains alive. The mystery becomes an invitation rather than a problem. Feynman's own teaching style reflected this philosophy. He did not aim to make difficult ideas sound easy by oversimplifying them. Instead, he tried to make them sound honest. He acknowledged confusion openly and showed that even experts live with unanswered questions. This approach reassured students that not understanding immediately was not a failure. Confusion was a natural response to ideas that challenge deep-seated intuitions. In the context of magnetism, this honesty reveals something profound. The force between magnets is not mysterious because we lack intelligence or imagination. It is mysterious because it arises from layers of reality that do not resemble everyday experience at all. Expecting a common sense explanation is like expecting a shadow to explain the object casting it. The shadow can tell you something is there, but not what it truly is. By challenging common sense answers, Feynman was not rejecting intuition entirely. He was refining it. He wanted intuition to be guided by evidence and mathematical structure, not by comfort. Over time, physicists develop a new kind of intuition, one that accepts abstraction and strangeness as normal. This intuition does not visualize magnets pulling each other with invisible hands. It understands magnetism as a consequence of deeper laws, even if those laws resist visualization. Ultimately, Feynman's challenge reshapes the question itself. Instead of asking why magnets work in a way that demands a familiar story, we learn to ask how magnetism fits into the overall structure of physical law. We stop demanding that nature explain itself in human terms and start appreciating it on its own terms. This shift is not a loss. It is a gain in honesty, depth, and wonder. In this light, the refusal of common sense explanations is not cold or dismissive. It is respectful of reality. It acknowledges that the universe is not obliged to make sense to us in the way everyday objects do. Magnetism becomes not a failure of explanation, but a lesson in how explanation itself must evolve. And in accepting this lesson, we move closer to the spirit of Feynman's thinking, curious, humble, and unafraid of answers that challenge the very way we think. When the mystery of magnetism is pushed far enough, it inevitably escapes the comfortable world of classical physics and drops into a realm where everyday language begins to fail. This is the point where quantum mechanics enters, not as an optional layer of complexity, but as the only framework capable of explaining why magnetism exists at all. What feels like a simple force between two objects turns out to be the large-scale echo of rules that govern the smallest constituents of matter, rules so strange that even physicists hesitate to describe them in ordinary words. At first glance, it seems reasonable to imagine magnetism as something built from tiny circulating currents. Early scientists pictured electrons orbiting atomic nuclei like planets around the Sun, generating miniature loops of electric current. These loops, when aligned, were thought to produce the magnetic fields we observe. This picture was useful and partially correct, but it was also deeply misleading. It relied on classical imagery that breaks down completely at atomic scales. Electrons do not behave like little balls following neat paths. They obey quantum laws that defy direct visualization. The real source of magnetism lies in a property of electrons called spin. The word itself is unfortunate because it invites the wrong mental image. Spin is not literal rotation. If an electron were actually spinning fast enough to account for its magnetic effects, parts of it would have to move faster than light, which is impossible. Spin is instead an intrinsic quantum property, something electrons simply possess, much like mass or electric charge. It has no classical counterpart, no everyday analogy that fully captures what it is. Despite its abstract nature, electron spin has very real consequences. Because electrons carry electric charge, their spin gives rise to magnetic effects. Each electron behaves like a tiny magnet, not because it is spinning in space, but because quantum mechanics assigns it a magnetic moment tied directly to its spin. This is not a metaphor or an approximation. It is a fundamental rule confirmed by countless experiments. Without electron spin, permanent magnets as we know them would not exist. However, the story does not end with individual electrons. In most materials, the magnetic effects of electrons cancel out. Electrons tend to pair up with opposite spins, neutralizing each other's magnetic influence. This is why most substances are not magnetic. In certain materials, though, something remarkable happens. The quantum rules governing electrons, combined with the structure of the material, cause many electron spins to align in the same direction. When this alignment persists over large regions, magnetism emerges on a scale we can see and feel. This alignment is not driven by a simple desire to line up like tiny compass needles. It arises from a subtle quantum effect known as the exchange interaction. This interaction has nothing to do with classical forces pushing or pulling electrons into alignment. Instead, it emerges from the strange requirement that electrons are indistinguishable and must obey specific mathematical rules about how their quantum states combine. These rules dictate that, in some situations, aligned spins result in lower energy than opposing ones. Nature favors lower energy configurations, and magnetism is born. What makes this especially unsettling is that the exchange interaction is not a force in the traditional sense. There is no particle flying between electrons carrying instructions to align. The interaction exists because of the way quantum wave functions overlap and the constraints imposed by the Pauli exclusion principle, which forbids identical electrons from occupying the same quantum state. Magnetism, at its root, is a consequence of identity and exclusion, not mechanical pushing. This is where Feynman's perspective becomes particularly illuminating. He often emphasized that quantum mechanics does not offer pictures, it offers rules. These rules are encoded in mathematics, and their predictions match reality with extraordinary precision. But they do not tell stories in the way the human mind prefers. When we say that electron spins align because of quantum effects, we are not unveiling a hidden mechanism that can be imagined. We are stating a rule that works, even if it resists visualization. Another layer of strangeness appears when relativity enters the picture. Magnetism is not an independent phenomenon separate from electricity. According to Einstein's theory of relativity, magnetic effects can be understood as electric effects viewed from a moving frame of reference. Charges that appear stationary in one frame may be moving in another, and the forces between them change accordingly. From this perspective, magnetism is woven into the fabric of spacetime itself. It is not an extra feature added on top of electricity, but a natural consequence of how electric forces behave when relativity is taken seriously. When quantum mechanics and relativity are combined, the result is even more astonishing. The precise value of the electron's magnetic moment, for example, can be calculated using quantum electrodynamics, one of the most accurate theories ever developed. The agreement between theory and experiment is so precise that it matches measurements to more than 10 decimal places. This level of accuracy suggests that, strange as these ideas may be, they are describing something profoundly real about the universe. Yet, for all this success, the explanation still feels unsatisfying to those seeking a simple why. Why should electrons have spin at all? Why should the laws of quantum mechanics take the form they do? At this level, physics reaches a philosophical boundary. These properties are not derived from deeper principles we currently understand. They are inputs to the theory, discovered through experiment and accepted because they work. Feynman was very clear about this point. When you reach the foundations, there is no deeper explanation waiting underneath, only more accurate descriptions. The role of quantum mechanics in magnetism, therefore, changes the nature of the question itself. The mystery is no longer about invisible forces acting across space, but about why matter is structured the way it is at the most fundamental level. Magnetism becomes a surface phenomenon, an emergent effect arising from deep quantum rules. The fridge magnet is not simple at all. It is the final link in a chain that stretches down to the identity of particles and the symmetry of physical law. This realization can feel disappointing at first. People often hope that deeper explanations will feel clearer, not more abstract. Quantum mechanics does the opposite. It replaces familiar ideas with probabilities, wave functions, and operators. It tells us what we can measure and predict, not what we can imagine. Feynman embraced this discomfort. He famously said that if you think you understand quantum mechanics, you probably do not. The goal is not comfort, but accuracy. In magnetism, this attitude is especially important. Any attempt to explain it using purely classical intuition inevitably fails. Tiny spinning balls, circulating currents, and invisible fluids all break down under scrutiny. The true explanation lies in a mathematical framework that does not translate cleanly into pictures. The success of that framework is not measured by how understandable it feels, but by how well it matches experiment. What makes this even more profound is that quantum mechanics does not merely explain magnetism. It explains why matter itself is stable. The same rules that give electrons spin and enforce exclusion also prevent atoms from collapsing. The solidity of everyday objects, the rigidity of materials, and the existence of chemistry are all tied to these quantum principles. Magnetism is just one visible consequence of a much deeper structure. Feynman often encouraged people to appreciate this interconnectedness. He believed that the beauty of physics lies not in simplifying nature to fit human expectations, but in discovering the unexpected unity beneath diverse phenomena. Magnetism, electricity, relativity, and quantum mechanics are not separate stories stitched together. They are different expressions of the same underlying rules. Seen this way, the role of quantum mechanics and electron spin in magnetism is not just a technical detail. It is a lesson in how reality is built. It shows that the forces shaping our everyday world arise from principles that do not resemble anything in daily experience. The universe is not constructed from familiar parts scaled down. It is constructed from abstract entities whose behavior only becomes visible when many of them act together. In the end, magnetism stops being a simple question about attraction and repulsion and becomes a window into the deepest layers of physics. Every magnetic interaction carries within it the imprint of quantum identity, exclusion, and symmetry. When two magnets snap together, they are not merely touching. They are revealing, in a quiet and ordinary way, the strange quantum architecture of the universe. And in recognizing this, we come closer to Feynman's way of seeing the world, not as something that must make sense to us, but as something whose strangeness is itself a source of wonder. Asking why feels like the most natural thing a human mind can do. From childhood, it is how we learn about the world. Why is the sky blue? Why does fire burn? Why does a magnet pull metal toward it? Each answer usually leads to another question, and we expect that if we keep asking long enough, we will eventually reach a final, satisfying reason. Richard Feynman argued that this expectation, though deeply human, quietly breaks down when we reach the foundations of physics. Magnetism provides one of the clearest examples of where and how this breakdown occurs. At first, the chain of explanation seems to work well. A magnet attracts iron because of magnetic forces. Those forces exist because of magnetic fields. Magnetic fields arise from electric charges in motion and from the intrinsic properties of electrons. Each step feels like progress. We move from a simple observation to deeper and deeper layers of description. But if we keep asking why at each stage, something strange happens. The answers begin to lose their familiar shape. They stop being stories and start becoming statements of fact without deeper justification. Feynman emphasized that this is not a flaw in physics. It is a misunderstanding about what explanations are. An explanation is never absolute. It always rests on assumptions the listener is willing to accept without further questioning. To someone who understands nothing about atoms, explaining magnetism in terms of electrons is meaningful. To someone who understands electrons, the explanation immediately raises new questions. Why do electrons have these properties? Why do they behave according to quantum rules? The moment you move to a deeper level, yesterday's explanation becomes today's description. This is where many people feel frustrated. It can feel as if physics is dodging the real question. But Feynman pointed out that the frustration comes from expecting an ultimate why that nature may not provide. Physics is built on laws discovered through experiment. These laws describe regularities in how the universe behaves. They are not derived from pure logic, nor are they chosen for human convenience. At the deepest level, the laws are accepted because they work, not because they feel inevitable. In everyday life, we are used to explanations that end in familiar experiences. A glass breaks because it falls and hits the floor. The explanation feels complete because we accept the behavior of solid objects and gravity as given. We rarely ask why matter resists deformation or why gravity exists at all. We stop asking because the explanation has reached a level that feels natural to us. But this feeling of naturalness is an illusion created by familiarity, not by fundamental understanding. When we apply the same expectation to magnetism, the illusion collapses. There is no level at which the explanation suddenly becomes self-evident in human terms. Magnetic fields are not intuitive. Quantum mechanics is not intuitive. Even spacetime itself, when examined closely, defies common sense. The chain of why questions does not end in a comfortable picture. It ends in mathematical laws that describe how nature behaves, and then it stops. Feynman often used simple analogies to make this point clear. Imagine asking why a chess piece moves the way it does. Someone might explain the rules of the game. If you then ask why those are the rules, there is no deeper answer within chess. The rules simply are what they are. You can study their consequences, master strategies, and predict outcomes, but the rules themselves are not explained by something more fundamental within the game. Physics, at its deepest level, works in a similar way. This realization forces a shift in how we think about understanding. Understanding does not always mean being able to visualize or justify something in terms of everyday experience. In physics, understanding often means knowing the rules and being able to apply them correctly. It means being able to predict what will happen, even if the reason feels abstract or strange. Magnetism is understood not because we can imagine tiny magnets pulling on each other, but because we can calculate magnetic effects with extraordinary accuracy. The limit of why questions becomes especially clear in quantum mechanics. Quantum theory begins with a set of postulates that describe how physical systems behave. These postulates are not derived from deeper principles we currently know. They are statements like, physical systems are described by wave functions, measurements yield probabilities, and certain quantities come in discrete amounts. Asking why these postulates are true leads nowhere within the theory itself. They are starting points, validated by experiment, not explained by something deeper. Feynman was unapologetic about this. He believed that pretending otherwise would be dishonest. Inventing philosophical or mechanical stories to make quantum rules feel intuitive only creates confusion. It gives the illusion of explanation without the substance. Better to admit that at some level, nature simply behaves the way it does, and our task is to discover and describe that behavior as precisely as possible. This attitude can feel unsatisfying, even unsettling. Humans want reasons, not just rules. We want to know why the universe is this way rather than some other way. Physics, as Feynman understood it, cannot answer that question. It can tell us how the universe behaves and how to test those behaviors. It cannot tell us why the universe chose these particular laws. That question may belong to philosophy, metaphysics, or theology, but it lies outside the reach of experimental science. Magnetism highlights this boundary beautifully. We can trace its origin from everyday attraction all the way down to electron spin, quantum statistics, and relativistic effects. Each step deepens our knowledge and expands our predictive power, but at the bottom, we encounter facts that simply are. Electrons have spin, quantum rules apply, spacetime behaves in a certain way. These are not explained within the theory. They are the foundation on which the theory stands. Feynman argued that recognizing this boundary is a form of intellectual maturity. It prevents us from confusing explanation with familiarity. It keeps science honest about what it can and cannot do. When we accept that some why questions have no further answer within physics, we stop demanding the impossible and start appreciating what science actually offers. There is also a strange kind of beauty in this limit. It suggests that the universe is not tailored to human understanding. Its deepest structure is indifferent to our desire for narrative closure. Yet, through careful observation and reasoning, we can still uncover its patterns. We can still use those patterns to build technology, predict phenomena, and expand knowledge. Magnetism, mysterious as it is, becomes a tool precisely because we know its rules, even if we do not know why those rules exist. Feynman believed that this perspective deepens wonder rather than diminishing it. If everything could be reduced to a simple, familiar story, the universe would feel small. The fact that reality resists our intuition, that it confronts us with limits to explanation, makes it richer and more profound. Magnetism is not less amazing because we cannot fully explain why the laws behind it exist. It is more amazing because it reveals how deep those laws go. In everyday life, it is tempting to stop at the first explanation that feels comfortable. North and south poles, invisible fields, attraction and repulsion. Feynman urged people to push past that comfort, not in search of a final why, but in search of clarity about where explanation truly ends. The point is not to eliminate mystery, but to locate it honestly. When we finally reach the limit of why questions in physics, we are not left with ignorance. We are left with knowledge of a different kind. We know the rules of the game nature is playing, even if we do not know why those rules were chosen. We know how magnetism behaves, how it arises from deeper laws, and how it fits into the structure of reality. That knowledge is powerful, even if it is incomplete. In this sense, the limit of why questions is not a wall but a horizon. It marks the edge of what physics can currently explain. Beyond it lies mystery, not as a failure, but as an invitation. An invitation to keep exploring, to refine theories, and to remain humble before a universe that is deeper than any single explanation can capture. Magnetism, simple and familiar on the surface, quietly leads us to that horizon and asks us to accept that understanding does not always mean having the final answer. When magnetism is finally seen in its full depth, it stops being just a curious force between objects and becomes something far more unsettling. It quietly reshapes how we think about reality itself. What begins as a simple childhood experience, two objects snapping together, ends as a confrontation with the way the universe is structured at its most fundamental level. This is where Feynman's perspective becomes most transformative, because he did not treat magnetism as an isolated phenomenon. He treated it as a clue, a hint that reality is not built the way human intuition expects. At the surface level, reality appears solid, continuous, and mechanical. Objects have clear boundaries. Causes precede effects in straightforward ways. Forces seem to arise from contact or visible connections. Magnetism violates this picture immediately. It acts through empty space. It does not require touching. It does not weaken in a simple, intuitive way. Instead, it obeys precise mathematical laws that care about orientation, motion, and underlying structure rather than direct physical contact. Even before quantum mechanics enters the story, magnetism already signals that the universe does not run on everyday logic. As explanations deepen, this signal grows louder. Magnetism turns out not to be a basic force in the way people imagine. It is inseparable from electricity. Electric and magnetic effects transform into one another depending on how you move relative to them. What looks like a magnetic force in one frame of reference can appear as an electric force in another. This alone forces a radical shift in perspective. Forces are no longer absolute things. They depend on how reality is observed. Space and time themselves participate in shaping physical effects. This realization erodes the idea that the universe is built from independent pieces interacting in fixed ways. Instead, it suggests a reality where relationships matter more than objects, where motion and perspective are woven into the behavior of nature. Magnetism is not something added on top of matter. It is a manifestation of how matter, charge, space, and time fit together. Reality begins to look less like a machine and more like a tightly constrained system of patterns. When quantum mechanics enters the picture, this reshaping becomes even more profound. Magnetism ultimately depends on properties of particles that cannot be visualized. Electron spin is not a thing you can point to or imagine spinning in space. It is a rule governing how electrons behave. This means that what we perceive as a force between magnets is actually the large-scale outcome of abstract mathematical constraints acting on countless particles simultaneously. This is a shocking idea when fully absorbed. It means that the solidity and reliability of the everyday world emerge from rules that do not resemble solidity or reliability at all. The magnet on your desk feels real, stable, and concrete, yet its behavior depends on quantum identities, probability amplitudes, and symmetry principles. Reality, at its foundation, is not made of tiny solid things. It is made of rules. Feynman emphasized that this is not a poetic metaphor. It is a literal statement about how physics works. The laws come first. Objects are secondary. What we call a magnet is not a basic entity. It is a stable pattern formed by matter obeying deeper laws. Magnetism is not a substance flowing between objects. It is a predictable outcome of how those laws constrain motion and interaction. This perspective reverses the way people usually think about explanation. In everyday thinking, we imagine objects as primary and laws as descriptions of how those objects behave. In fundamental physics, the laws are primary. Objects are what happen when the laws allow certain stable arrangements. Magnetism is not explained by the magnet. The magnet is explained by the laws that permit magnetic order to exist. Once this shift occurs, reality starts to feel less intuitive but more coherent. The universe no longer seems like a collection of independent things occasionally interacting. It appears as a single, interconnected structure, where changes in one part reflect deeper constraints imposed everywhere. Magnetism becomes one expression of this unity, a visible sign that the same rules apply from subatomic scales to human experience. This reshaping also affects how we think about causality. In classical intuition, causes push effects forward through space. Magnetism does not work that way. There is no signal traveling from one magnet to another in the way a hand pushes a door. Instead, fields describe the conditions of space itself. Objects respond to local conditions, and those conditions reflect the presence of other objects. Cause and effect are still there, but they are distributed through space rather than localized in contact. At the quantum level, causality becomes even subtler. The alignment of electron spins in a magnet is not the result of one electron sending a signal to another to line up. It arises from global constraints on how identical particles can exist together. The cause is not a push or a pull. It is a limitation. Certain arrangements are allowed, others are forbidden. Reality unfolds within those boundaries. This forces a reconsideration of what it means for something to be real. Is a magnetic field real if it cannot be seen or touched? Feynman would say that reality is defined by what has measurable consequences. Magnetic fields shape motion, transfer energy, and store information. They are as real as anything else in physics, even if they do not resemble matter. Reality is not limited to things you can hold. It includes patterns, relationships, and constraints. Magnetism also reveals that simplicity at the surface often hides complexity underneath. A bar magnet looks uncomplicated, yet explaining its behavior requires some of the most sophisticated theories humans have ever developed. This inversion challenges the assumption that simple appearances reflect simple causes. In fact, the opposite is often true. The stability of the everyday world depends on layers of complexity arranged just right. Feynman believed that this realization should not be discouraging. It should be exhilarating. It means that every ordinary experience contains hidden depth. the world is not shallow. It is profoundly structured. Magnetism is a reminder that reality is not exhausted by what we immediately perceive. There is always more going on beneath the surface. This perspective also reshapes how we think about knowledge itself. Knowing something does not always mean being able to picture it. In physics, knowing often means being able to calculate, predict, and test. Magnetism is known because we can predict exactly how it will behave in countless situations. That knowledge is precise and reliable, even if it defies intuition. Understanding becomes less about mental images and more about grasping relationships. Feynman warned that insisting on intuitive pictures can actually block deeper understanding. When people demand that magnetism be explained in familiar terms, they risk rejecting accurate explanations simply because they feel strange. Accepting that reality may not align with human intuition is a crucial step in scientific thinking. Magnetism trains the mind to make that leap. Over time, this training changes how one sees the world. Reality stops looking like a stage filled with objects and starts looking like a network of laws giving rise to patterns. Magnetism, electricity, light, and matter all become variations on a single theme rather than separate phenomena. The boundaries between forces blur. The universe feels more unified, even as it becomes less intuitive. There is also a philosophical consequence. If reality is governed by abstract laws rather than mechanical pictures, then the question of why shifts meaning. Why does a magnet attract another magnet? Because the laws of physics are such that this interaction occurs. Why are the laws that way? Physics cannot answer that. It can only tell us what the laws are and how well they work. This does not weaken science. It defines its scope. Feynman saw this not as a failure, but as honesty. Pretending that physics can answer ultimate, why, questions only leads to confusion. Magnetism teaches us where explanation ends and description begins. It shows that reality does not owe us reasons in human terms. It owes us consistency, and it delivers that in abundance. At the same time, magnetism deepens wonder rather than diminishing it. The idea that invisible quantum rules give rise to tangible forces is astonishing. The fact that abstract mathematics maps so precisely onto physical behavior borders on the miraculous. Reality turns out to be intelligible, even if it is not intuitive. That balance between mystery and comprehension is what makes physics so powerful. In the end, magnetism reshapes our view of reality by revealing that the universe is stranger, deeper, and more unified than it appears. It shows that everyday experience rests on foundations far removed from common sense. It teaches that explanation does not always mean comfort, and understanding does not always mean visualization. Through magnetism, we glimpse a universe where laws come first, objects come second, and human intuition is only a small window into a much larger structure. This is the quiet revolution Feynman pointed toward, not a dramatic shattering of reality into chaos, but a gentle dismantling of assumptions we did not realize we held. Magnets do not just stick together. They invite us to rethink what it means for anything to exist at all.